This is the fifth lecture in Z-transforms. It's a bonus material taken outside of Chapter 5, but Chapter 5 concepts are going to let us work our way through it. We're going to look at how we can use Z-transforms to solve finance problems. Typical finance problems include things like loans, consumer loans. It can also include things like how we save in our retirement accounts and prepare for retirement. I'm going to introduce this use of Z-transforms to solve finance problems through a loan type of problem. I'm going to do it a little bit with a story. Try to keep this related to stuff that I think we can all appreciate. Um, all of you are working towards a degree. We're going to go ahead and think about a student seen there right in the middle. That student just got their diploma, their Bachelor of Science in Electrical Engineering. So they got their hands all up, happy and excited. They've got that degree in hand. They're ready to go out and spend their new job money. Go into that new town. They need to get a new place to live, so they got their eye on this beautiful home and wanna go ahead and make an offer on it. Turns out though that home, right, costs a little bit of money. In fact, it's quite a bit of money. For the time being, we're going to go ahead and let this home be a little on the expensive side, just so that we can illustrate some principles. U.S. median household income right now is probably in the 50 range. Our students do well, so let's say that our students are well exceeding that. Maybe they're making 100,000 a year. Median house price in the U.S. is approximately $200,000. This overachieving student has decided to go double that, so they've got their eye on a beautiful house that's about $400,000. Problem is, well, that diploma in electrical engineering didn't come cheap, and so this student's pockets are pretty empty. Those dollars that we need, the $400,000 we need for that house, student just doesn't have it. They've got pennies in their pocket because they paid all of their money to get through school, and so the question becomes, how in the heck do we get that house? Well, the whole entire U.S. finance industry is set up for this, and this student happens to go to, well, where else? Honest Greens Loans. So Honest Greens Loans is going to help the student negotiate this loan problem and figure out what his payments are going to be every month. So we've got the context for this guy. We just need to see if we can solve it using our knowledge of Z-transforms and discrete time systems. So let's go ahead and get started on this. This is all along the lines of the loan problem. So we are looking at solving the basic loan problem. And I'm going to keep it all in context of this current story. So a student buying a house for $400,000 and wanting to figure out what they're going to owe on a monthly payment, make sure it fits within their income that they're getting from their new engineering job. The loan problem, we need to get a model going, and so I'm going to just return to what we've been looking at throughout this class, which is that we've been looking at systems where there is something, right, that operates on an input. So I have my input going in, and then we have an output coming out. And I want to think how I can apply this system model to the loan problem. What would be my input? What does a consumer put into their loan? Well, they put in their payments. So we can look at the input here to our finance system here as being the payments to try to pay off that loan. This system, the block in there, is what generates the output, which is going to be the actual loan balance. So we have a loan balance, right? The amount of money that we owe, and we are going to pay into it some monthly payments, most likely, to try to pay off that loan balance. And then there's a system that operates on that payment as well as previous loan values to figure out what the current loan balance is. So we do have a basic block diagram here that could be consistent with this loan problem. We'd like to go ahead and make sure we've got a good sense of all the variables. Let's take a look at this time variable n. N here is discrete time, so we're going to be looking at discrete instances. We're going to consider this a traditional loan problem where you make payments every month. And so N here is really just going to designate the month. So we are going to let N designate the month because most things like house loans or car loans, even a lot of interest rates going into things like savings accounts are done on a monthly basis. So we'll let N represent month. Doesn't have to be that way. We could certainly have loan type problems that would be addressed on a different kind of time scale. There might be ones that are dealt with daily. There might be ones that are dealt with quarterly or just yearly. In this particular case, we're going to keep with the standard though of monthly. So N is going to be our month. Okay. We do know that the consumer, in this particular case, the student, needed to get some amount of money so that they could buy that house. Now, of course, they won't own the house outright, but they're going to borrow the money so that the person selling it has their money. And then they're going to make payments to the bank, right, to try to get it so that they can have that house free and clear. So initially, the bank is going to give this consumer some money. We're going to call that the initial condition, y of -1, and that's going to be the loan amount. So this particular person is trying to seek a loan for a particular object or a desired product, in this case, a house. The cost on that, we said in this particular case, was going to be equal to $400,000. So we were going to go ahead and look at a house that was double the U.S. median house price. So get a nice house out of this, $400,000. That's going to be our amount that the bank gives the student. So we can think about that as a loan amount. Depending on how you wanted to carry this out, you could have operated with, like, something where it says the net value to the student, and maybe the net value to the student would be minus 400,000 now. But because I'm calling it a loan, we know loan means an obligation of the student. So I'll just leave that as a positive 400,000 for right now. Our goal is going to be to reduce that 400,000 down to zero, so that the house will be paid off. If we think about that loan amount being paid out at that month -1, well then let's say N equals 0 is what? This is the month, if you will, when our first payment is going to be due, when the first payment is due. You usually get a loan and then you immediately start paying. So we're going to keep this standard. You could certainly look at other situations. It's notorious in industries like, let's say, furniture stores. They might go ahead and give you the loan for the furniture. You send it in a truck to your house, and they defer the payments for 6 months. That would require a little bit different model, but for right now, we're just going to stick with a standard kind of loan. So N equaling 0 is when the first payment is due. We'd already said that Y of N itself, right, is the loan balance. It is the loan balance at some time or month, in this particular case, at month N. When we first get the loan, Y of -1, so 1 month before the first payment, right, the loan balance is just $400,000. When we go forward 1 month, though, we know that we're going to owe a little more than $400,000 because people don't give us money for free. They need to justify the risk and make a little money in providing us that value. And so there is some interest rate charged in here as well. So let's take a little aside and talk about interest rate. We know that interest rates are just a real fact of any kind of loan instrument. So interest rates, and I'm going to ask you a couple questions. Think about your own life. Let's look at something like a credit card. Okay, so credit cards are a type of loan instrument. Almost everybody has a credit card of some sort, and I'd like you to answer the following question: What is the interest rate? The interest rate of your credit card. Okay, so just jot that down. Jot down that number of what is the interest rate of your credit card. What I can tell you on this is that this is not like a hard problem, but it's one that you either tend to know or you don't know. If you were able to write down a number, well, then you are doing better than over half of the U.S. population. So, and it's even worse than that. There's a basic little fact here that there is less than 50% of balance carrying. So these are not just people with credit cards, but people who have credit cards and have an ongoing balance on it. So 50%, under 50% of balance carrying credit card users know their interest rate. Interest rate. This is actually a really scary statistic. If you don't know the rate that you're even paying, you're certainly not going to be able to manage or control or figure out how to plan a smart way of dealing with those loan balances. So less than 50% understand or know their interest rate. Um, a typical credit card would be something that might be in the low sixes all the way up into the mid 20s, something like a 28%. It could certainly go outside of this range. I think very typical for young investors or young borrowers that don't have an established credit history, that you'll be paying on the higher side. And so I think at least from a student standpoint, it would be more in the 15 to 25 percent rate for a typical student on this. So we do get some pretty substantial rates, at least associated with credit cards. Second question on this, okay? We can talk an interest rate, something like 15 to 20%. For right now, I'm just going to go ahead and assume something. I'm going to go ahead and assume, oh, let's just be generous today. Let's make it a low percent. Let's say your credit card was 12%. 12% what? Okay. Interest rates aren't just a single thing. There's many ways that lending institutions, banks, or credit card companies will present their rates, and we can see whether on this particular case. So two typical figures in here is something called an APR. So an APR is one typical one, APR, and another one that is very typical is an APY. So let me ask you this. You have your credit card, you either knew or didn't know your interest rate on it. Assuming that you do know your interest rate or that you could look it up, is it an APR on your credit card or is it an APY on your credit card? Again, I will say that the average American consumer oftentimes doesn't know the difference, or certainly wouldn't be able to give a mathematical way of working through the differences between these two figures of APR and APY. I can almost guarantee you that your credit card will be expressed in this form APR. And I will almost guarantee you that when it comes to you trying to understand what it is that you're going to owe later, that you really need it as an APY. So if you don't understand the difference between this figure of APR, annual percent rate, and this other figure, APY, annual percent yield, you're definitely going to probably have difficulties making good sense of what your loans are and how much you're actually paying for it. So let's take a few minutes and make sure that we understand this difference between APR and APY. I'm going to start out with this APR. A typical credit card expresses its loan or its rates in terms of APR, annual percent rate, and we're going to go ahead and work with this value of 12%. This is going to be a credit card that's operating in the typical way credit cards do, which means that interest is going to be calculated monthly and payments are expected monthly. So here with a credit card, so if I have a credit card, we're going to be doing things monthly. So it's a monthly instrument, right? Instrument. And so over a year, right, there's 12 months. So 1 year equals 12 months, something along those lines. The annual percent rate, annual just means yearly, right? But the thing that is happening monthly. And so we need to somehow get that annual part down to a monthly part. Here's the way APRs work. If you take a look at an APR looks like this. An APR says we take the periodic rate, and in our case, this is going to be monthly, the monthly rate, because that's the period we're operating on, times the number of periods per year, something like that. So if I was going to convert that in this particular case, we know that the APR was 12%. That's going to be some periodic rate times 12 months, right, per year. So I can get my APR, the APR of 12%. Well, there's a reason I picked 12% on the left side, because I know 12 by 12 is something really simple. So my monthly rate here, my monthly rate is equal to 1%. Okay, so a 12% APR charges 1% per month. That's just the way the math works out. That's the way they design these instruments. Why is this a little bit misleading? Well, because after the first month, when they charge you some interest, when it comes to the next month, they charge you interest not only on what you originally owed, but they also charge you interest on the interest. This is the compounding phenomenon. And so when it comes to the end of the month, you're not going to just owe 12%, you're going to owe something more. So let's do an example of that as well. Suppose you borrow $100, okay? You borrow $100 on January 1st at 12% APR, something along those lines. That $100 on January 1st at 12% APR, we're going to make no payments whatsoever. We're just going to go from that January 1 to January 1. Well, let's just make it easier. Let's make it go to December 31st. We'll call that the full year. So through December 31st, and I want to know, what is my balance? What is my balance? Right? How do I get that? Well, January, right? 1, I owe $100. February 1, what do I owe? I owe $100, right? Times, right? 1.01. The first one, right, keeps the principal, so we have to not get rid of the principal. Whoops, got that misspelled, so we're going to go ahead and put that again. So we have our principal, principal amount, and then that 0.01 is the interest, right? So if I take $100 times 1.01, I would have $101 that I would owe. That makes sense. We were charging 1% per month. 1 month is gone. We had $100, so we should owe $101. What happens in March 1st? We are going to have our previous month's balance, 101, and we need to multiply that by 1.01. If I go ahead and pull out a calculator on this, I'm going to go ahead and put in the 101, and I'm going to take a 1.01 and multiply it. And what I find out is that I get on this one, right, I'm going to get a 102.01. So it's not just one more dollar, it's a dollar and a penny more, right? That extra penny came out of interest on the previous month's interest. And we can keep going that way till the very end. And what we find out here is, what do we get? We get the original amount, $100, each time, every month that occurs. We're multiplying it by a 1.01. There's 12 months per year, so I'm going to raise that to the 12th power. If I go ahead and do that in my calculator, I'm going to put a 1.01, enter that in, take a 12-month total set of periods in there, raise it up to that, and what I get is I'm going to get, in this particular case, $100 times the factor of 1.1268, something like that. And that's going to give me what? It's going to give me $112.68. I want to compare that to what many people would have considered on this. A lot of people who don't really fully understand the idea of annual percent rates would sit there and say, hey, there's $100 at 12%. I'm going to have it for a year. So what is 12% of $100? It's $12. So I should owe $112. And it's not, right? We owe $112.68. We almost owe $1 more. It might not seem like a lot in this particular case. The loan period's pretty small. The original balance was pretty small. But 68%, right? That's about 8 or 9% of the total amount of interest that otherwise would have been done. If you want to think about what the actual yearly rate is, how much did I get? How much did I get, or how much did I pay in this case? How much did I actually pay? Did I actually pay? Actually pay? Well, that's the annual percent yield factor. And in this particular case, 12.68%. Annual percent yield is almost always higher than the APR. And that's why credit card companies don't express their rates in terms of APY. Who in their right mind is going to go out and take a loan, right, where the number they're given seems bigger than what another place is doing? However, if I was going to take this just as another one, if I was going to sit there and say there was one credit card that gave you an APR of 12%, which we know is just disguised for the actual yearly amount that you would owe of 12.68%, that's really what it means. And there was another credit card company that decided to try to give consumers a more meaningful value, annual percent yield, and they read it out here as 12.5%, right? 12.5% APY is actually a better deal than that 12% APR of credit card company number one. So here was company number one, here was company number two. The vast amount of Americans, though, the vast amount of Americans, world people doesn't really matter, are going to see that lower number, 12%. Whoops, not that one. They're going to see that's that smaller number of 12%, and they're going to compare that to the other company's 12.5, and they're going to select that 12% APR, even though in the end they would pay more. It's just not understanding the instruments themselves, how these loan values are done. Okay, so where were we in all of this? We're going to go back just a little bit. Remember what we were doing. We were working on this student buying a home, right? Going to borrow some money from Honest Green Loans. We were trying to set up some idea that we were going to look at this loan problem in terms of a signals kind of perspective. N was our month. Y of -1 was our initial loan amount, which was $400,000 in this case. N equaling 0 was when the first payment was due. You wouldn't have to do it that way, but it's convenient for the way we have things set up in this class. Y of N is the loan balance due on a particular month, and we were trying to figure out what kind of interest would be typical or that might be charged on this loan. So we need to get back to this loan, and we want to think now back to our home loan, our house or home loan in this case. And if you remember, we had Y of -1 equaling 400,000. When you go in and negotiate a loan, one of the things you're going to negotiate is the interest rate. Interest rates are lower for people who have established credit, who are credit worthy or low risk individuals to rent or to loan to. People who have less history, like students, or those who just have not been as responsible with their money, are going to typically pay higher, which is sort of ironic. The people who can least afford it are probably going to pay more. Home rates are pretty low right now, but this student doesn't have a great established credit history, and so we might sit there and say that we don't fully know that they are going to qualify for that best rate. And just for simplicity, I'm going to go ahead and do it as that 12% APR. This would be pretty high. This would be a high loan even for a pretty moderate credit risk person, at least in today's market. Back in the 80s, though, actually, some of these home loans were getting up into the upper teens, almost up to 20%. It's one of the reasons why people had such a tough time affording housing back then. But let's take it as a 12% APR. What do we know 12% APR went to? That was a 1% per month, right? And we knew that that corresponded to an annual percent yield, right, of 12.68%. If you made no payments in there, what you would owe at the end of the year would be 12.68% of the original loan balance. So in this case of $400,000, if I went ahead and went into my calculator and put in a total of $400,000, entered that in, and then I multiplied that guy by 1.1268, multiply that out, we would owe after that first year, if we were making no payments whatsoever, right? So if we let this 400K go 1 year with no payments, right? With no payments, we would owe 400K, right, times 1.1268, which would give us, in this particular case, a $450,720 balance, something along those lines, $720 balance. So in this particular case, a 12% APR, right, is going to end up costing us about $50,000 a year. That does tell you something about what your minimum payment is going to be. If you were just going to break even, never start paying off any part of this loan, your payment would be that 50,000 divided by 12, right? That amount of interest as a rough first estimate, something along those lines. And that'd be about 4,000 a month. So we're going to just tuck that away in the back of our minds. I'm expecting that our payments are probably going to be at least around that 4,000 a month, just so we can break even. Okay, so how do we set this up so that we can use our Z-transform stuff? We need an equation at some point, and so let's start building our equation model. The loan balance at a particular month depends on what? It depends on the previous month's balance. So I take the previous month's balance, right? And then I'm going to multiply that by a factor that includes the interest rate and also the principal, something along those lines. I'm going to call that factor P. So factor P is going to be principal plus monthly interest. So in our particular case, P would be equal to what? It would be 1.01. The 1 for the principal and the 0.01 for the monthly rate, right? Because we were doing things compounded on a monthly period of 1% per month, which corresponds to the 12% APR, which is the same as 12.68% APY, something along those lines. So if nothing else was going on there, I would just accrue not only the principal, but I'd get some extra amount of that interest rate in there. So the new loan balance would be the old loan balance multiplied by this factor P. Of course, that's not all that's going in here. We are going to subtract off whatever we pay on month end. And so it's not just interest accruing, but we should also be reducing the amount we owe by what we are paying to the bank. So this input X of n is going to be our payment scheme. So now we're getting somewhere. We knew that Y of n was equal to the loan balance, right? We have our loan balance in there. Loan balance. We know that X of n now is our payments. It's our payments to the loan. And I think we can come up with a reasonable model on that as well. In this particular case, we might say that the payments are some amount C, right? And we might do that as a U of N minus U of N minus L. What does this mean? I'm going to pay C dollars over a total of L months. So I'm going to pay a fixed, right? C dollars per month for L months. We're going to start that, right? We start at n equaling 0, and we will end at n equaling L minus 1. The U of n, right, minus U of n minus L returns back to 0 at n equaling cap L, something along those lines. If I was going to sketch that out, I think it would make some sense, so I could throw my sketch in here as well. I'm not going to be paying anything on a loan before I've got it, so no need for that. But starting on that first payment date, that first month, which we called month 0, I'm going to pay C dollars, and I'm going to keep paying C dollars for however many payments that I've got. I'm going to keep doing that out until I hit L minus 1, right? And then I hope that I'm done. I no longer have to pay anything to the bank. So this is a very standard way of paying off loans. It's a fixed payment scheme over the duration of the loan. So we get another parameter in here. Cap L equals the number of months for our loan, something like that. What's a typical home loan? A typical home loan is like 30 years. So we're going to go ahead and put this student on a 30-year loan. So if I wanted L is going to be, because L is the number of compounding periods here are months, we're going to get 30 times 12. If I go ahead and carry that calculation out, we know that there's going to be quite a few payments in this particular case. There's going to be 360 different payments. So they're going to be paying this loan for a total of 30 years, once a month, right? 30 years, 360 total payments. Back to our equation then. We have our loan balance, Y of n, being equal to something, right, based on our previous low balance, minus X of n, where we now know that X of n, right, is equal to some amount C. That's the thing we don't know. That's what we're going to try to figure out. U of n minus U of n minus L, something along those lines. And we said that P here, right, for us was going to be equal to something like 1.01. If I wanted to do that in a more general sense, I might say that that guy is going to be 1 plus some interest rate I, that's a fractional amount, raised to the 1/12, where I is the fractional, it's the percent for our APY, the total amount in there. So let's try that calculation out here in this particular case. We said that our loan had an APY of 12.68%. As a fraction, that's 0.1268. I'm going to add that to the 1, so I here, right, is the 0.1268. That's the APY, and I'm going to raise it to the 1/12 to get it to the rate that can be compounded monthly. I'm going to go ahead and put that on my calculator. You could do it on your own. So 1.1268. Going to go ahead and enter that. I'm going to take 1/12. So if I take my 1/12 in there, and then I'm going to raise those two together, and I get exactly what I expected. I get a 1.01 on there. So it's a 1% accumulation every single month, and we also maintain the principal, something along those lines. Okay, so what do we want to do? We need to calculate C, right? C is our monthly payment amount. We would like to be able to calculate that. So we'd like to be able to calculate that monthly payment amount. So we have an equation that describes our system. It has some known input, although an unknown scale factor on it, and we would like to be able to calculate that in some particular way. Before I do that, I'm going to take another aside. I want to look a little bit about some properties of this system. So let's just look at some properties of this loan system, something along those lines. We know that the loan looked like what? I'm going to just do it for this particular loan. So this was y of n, right, equals 1.01 y of n minus 1, right, minus some x of n. If I drew that in a standard constant coefficient linear difference equation form, in standard form, it would be something like what? I would have 1, right, minus 1.01, right, e to the minus 1, put it in a delay form, y of n being equal to minus x of n. This first factor out front we know is our characteristic polynomial. That's that q. So here's a question for you. Is this system stable? Is this system stable? We've spent a bunch of time in this class talking about the importance of system stability, that virtually every system of engineering interest is stable. Some funny things happen in finance. If we go back to this guy and we think about stability in this particular case, the characteristic equation, if I was going to find the characteristic roots, I would put in gamma for E, and I would have 1 minus 1.01 gamma to the minus 1, set that equal to 0. Solve that guy for gamma. I get gamma equals 1.01. If I look then at the z-plane, right, go ahead and put this into the z-plane. I'm going to go ahead and put the unit circle for reference. And what I see is that my root is just a little outside the unit circle. It's a little outside the unit circle at a location 1.01. So we know the rules for stability. This system is unstable. Okay, it's a useful system, it's a useful finance system, but it's absolutely unstable. What does that mean? What does that mean to us, and is it something that we believe in? Is it something that makes sense to us? Think about our loan. We had a loan amount, y of minus 1 equaling 400,000. That's our initial condition. If we make no input, right, then that initial condition would just generate an output. So we could take that, right, this input of y of minus 1 with this initial condition y of minus 1 with 400,000 with an input x of n equaling 0. And then we could think about what is the zero input response of this system. We had spent some time solving that particular guy, and we know it's some scale factor, call it k, and we have our mode 1.01 raised to the nu of n, right? It's just a sum of modes. And because this system is unstable, because that mode is greater than 1, what do I expect that zero input to look like? It started out at minus 1 at $400,000. And because this factor here is greater than 1, it's going to just grow, right? It's going to keep growing, and it's going to grow exponentially. What does this mean? This means that if you never pay your loan, if you never make payments to your loan, that the balance keeps growing without bound. We would expect that. If it was a stable system, if you could somehow negotiate this, if you could somehow make your zero input, what does this mean? It means you go to Mexico and you don't pay any amount of your loan. So if I had a YZIR of n equaling, for example, a K with some stable system, let's just put it 1/100th on the inside of the unit circle, something like that, U of n. What would this system's behavior be? This system's behavior would be you put out and you get that $400,000 loan. You make no payment, but because it's a stable system, right, it exponentially decays. That means the loan pays itself. Wow, I would love a loan like that. I would love a loan that pays itself, but we know for a fact, we know that that is just not real life. We are not going to get loans paying themselves. If we don't make our loan payment, the loan balance grows and it keeps growing until people have a real incentive to come and track us down wherever we might be and shake our pockets out to get the money. So we do expect this to be an unstable system. Let's go back to the z-plane for just a minute and think again then about this system. And again, put the unit circle in there for reference, and I've got a pole. This loan problem is a first order constant coefficient linear difference equation. It has a single root. That single root's location, the location there depends, right? It depends on the interest rate, right? It depends on the interest rate. In our particular case, we had this as 1.01. It's that 1% per month, right? Which gave us a 12.68% APY. What are the forces going on in this? Well, the lender, right? The lender wants to pull the pole this way. So the lender grabs that root, and that lender wants to pull it as far away from the unit circle as possible. Why? Because that means they get more money from you every single month. The interest rate is higher. If we think about the borrower is trying to fight that interest rate to get as close to the unit circle as possible. They want to pay as little interest as possible. Whoever wins that tug of war, or wherever that tug of war brings us, is what the overall interest rate is going to be. That's that location. For us, it was a 1% per month interest rate. But this is a tug, right? It's a tug of war. Sometimes lenders have the upper hand in times of financial, kind of constriction, or where money's just a little bit tight, where risks are a bit high. They're going to be pulling a little bit harder. In other times, when there's other options available to consumers, those consumers are going to be able to pull a little bit more. And we certainly see this dynamic play out. Okay, it doesn't seem like we've gotten very far, but we've actually made quite a bit of progress. We're going to work now in trying to find that constant C that would reflect the payment amount for this particular loan. So in this particular case, I would like to go ahead and say, so we already looked at the case of whether this thing was stable or not, right? What is the amount that we are going to pay? What is the C monthly payment we need? How do we solve for that? Monthly payment? Well, let's return ourselves to the input. X of n is equal to C times some U of n minus a U of n minus L. That was our uniform payments over the loan duration, total of L payments, something along those lines. I'm going to write this in a slightly different way. There's no real particular insight as to why I'm doing it this different way. It's because I know where I'm going with this. This is not something that you're going to have to do typically. You're going to get some homework problems later with some loan type problems or savings type problems. It's unlikely you'll need to make this kind of substitution, but for this problem and trying to find this value C, this turns out to just be handy. So I'm going to write this in a slightly different way. It's going to be C times, I'm not going to write it as a bunch of, I'm not going to write this as a difference of unit steps. I'm going to write this as a bunch of delta functions. So I'm going to go ahead and let this be a sum going from 0 to L minus 1, a total of L, right? And I'm going to have just all of those different delta functions, each with some weight C. So these two expressions are the same. C times the quantity U of n minus cap L can be represented as a C times the summation from 0 to L minus 1 delta N minus I. If we just remember again what this thing looked like, right? We had our first one coming at 0 and it keeps going out until I hit L minus 1. What do we get? A value C, that's the C scale out front, and then I've got a total of L, right, values that are multiplying that C. I can write that as a difference of 2 unit steps, or I can just individually bring them out, all of those little delta functions, each one shifted one more to the right than the previous one. Okay, so that's my X of N. I would like to be able to then go back to my difference equation, which was what? It was a y of n in our particular case. And let's leave this in terms of p for right now. That way we can substitute later for whatever we wanted. So we have y of n equals a p y of n minus 1 minus x of n. I want to be able to do some solving of this guy. I'm going to apply my z transforms. Finally, we're getting some z transforms in here. If I go ahead and do my z transform on this, what do I get? I get y of z. Because it's a problem with initial conditions, we better do a unilateral transform in here. And I'm going to get what? I'm going to get a p times, well, a delay by 1 is just z to the minus 1 y of z. But then I also have that dependence on the initial condition. So this is going to be that little y of minus 1. And then I'm going to have a minus and the transform of my input x. So I would have my x of z somewhere along those lines. We're going to clean this up just a little bit. I'm going to bring all the y terms over to the left-hand side so I can solve for y of z. That's going to be y of z, and it's going to be multiplied by a 1 minus p z to the minus 1, something along those lines. On the right-hand side, I have little y of minus 1, right? And then I'm going to have the transform of x. But what was x? X was just a scale, right? It was just a scale in here of a bunch of shifted delta functions. What is the transform of a shifted delta function? That's a problem we looked at before. A shifted delta function just gives me a power of z, negative power of z if it's shifted to the right, which it is in this case. So the transform there is real simple. I'm going to get a minus c summation I equaling 0 to L minus 1. The transform of a sum is the sum of the transforms, and the transform of a shifted delta function is what? It's just z to the minus I, where I is that shift. So taking the z transform of that alternate expression for our input is really quite straightforward in this particular case. I forgot one factor in here, so I almost violated my own rule here. Take a look at this factor p, right? It weighted that entire y of n minus 1. I z transformed all of that there. That p should have also multiplied that initial condition. So I had forgotten to put that in there. Let's make sure we get that guy in there. If I solve now then for y of z, what do I get? I get y of z is equal to p little y minus 1 minus c summation I equaling 0 to cap L minus 1 z to the minus I over a 1 minus p z to the minus 1. Okay, so this should give me the transform domain expression for my loan balance. And I wanna do some thinking about this. And it's this thinking. It's a little bit out of the box thinking. This thinking is the key to solving this problem. What I'm going to look at is I'm going to look at this denominator term. This expression for my loan balance, y of z, seems to have a denominator here. So y of z seems to have a denominator that has a pole, right? If I can get that in there, with a pole at what? Well, if I solve that 1 minus pz to the minus 1, set it equal to 0, I get a z equaling to p, okay? It seems to have a pole at z equaling p. If I invert z transform that guy then, what do I expect? I expect something like a p to the n u of n type term to come out as part of my y of n being equal to, there might be some stuff there might be some other things, who knows. But we would expect, if there's a pole, we expect that pole to come out and show up as that pole raised to the n u of n. I'm going to suggest that this is completely unacceptable for our loan balance. This would suggest what? This would suggest that the loan balance, it suggests that y of n, right, does not equal 0 for all n greater than or equal to L. When I supposedly pay this thing off, it cannot be 0. Not if I have a term like this decaying or growing exponential. I cannot have that loan paid off. I can't have a loan balance that would be 0 after I was done paying off if that overall transform, if that transform domain solution for my loan balance really does have a root at location P. So let's go back here and look at this guy. We've got something. It's got a numerator and it's got a denominator. This denominator suggests some everlasting exponential as part of my balance. I know that's inconsistent with paying it off. And what that tells me is that I had better make this numerator have a 0 that covers up that pole. That's what's going to be the thing that I need in order to solve this problem. So to avoid, right, to avoid this problem, this contradiction, this way of never paying off my loan, I'm going to place a 0 to cover, if you will, to cover or cancel, to cancel that apparent pole, right? Apparent pole at z equaling p. So what was the numerator? The numerator was py minus 1 minus that c sum stuff. So let's go ahead and write that down. We had little py of minus 1, right? And then I had a minus c summation I equaling 0 to L minus 1 z to the minus I. That was my numerator. I want that such that when I evaluate at z equaling p, right, that it evaluates to 0. If I evaluate the numerator at some point and it gives me a 0, that's the definition of a 0. And if I make it evaluate to 0 at the same places there is a pole, that means that I've made the system have a 0 cover up that pole. It'll cancel it. So let's see what happens in that particular case. I end up with an expression like this, py of minus 1, right? I'm going to bring that c sum term to the other side. So this whole thing is going to be equal to c summation I equaling 0 to L minus 1. And z was just put in as p. So I'm going to have a p to the minus I. That sum on the right-hand side looks like a geometric sum. So I'm going to get C, right? And then it's a geometric sum where the geometric sum's ratio is going to be p to the minus 1, right? So the first term in that geometric sum solution is going to be 1 by p raised to the lower limit. And I'm going to subtract off 1 by p to the upper limit plus 1. So L minus 1 plus 1 is L. This is just our geometric sum solution. And then I'm going to have 1 minus the ratio 1 minus 1 by p, something along those lines. And that whole thing has to be py of minus 1 if I'm going to cancel out that pole. This is the thing that's going to ensure that I'm able to pay. There's only one thing that's unknown here, right? I know what is this interest rate that was given. I know what the initial loan balance was. That was given. This interest rate is still there. The total loan duration is there. This stuff is all there. This whole piece is known. The only thing that I don't know in this particular case is that value C. So let's solve for C. We are using C, right, to place a 0 to cover the pole of the system so this loan balance can become 0 after our loan duration of L payments. So which C allows us to do that? I just need to solve for C. Let's clean up one more time before I actually do that. Py minus 1 is equal to C times anything raised to the 0 is just 1, right? So I'm going to have 1 minus, and I'm going to have P to the minus cap L over, right, over here, a 1 minus P to the minus 1. Solving this guy for C looks something like this. C equals, I'm going to have py of minus 1, and I'm going to have a 1 minus p to the minus 1 over 1 minus p to the minus L. Maybe I just want to clean this up a little bit. I can take the first p outside, multiply it by the numerator there. I'm going to get a y of minus 1, and I'm going to get a p minus 1 over 1 minus p to the minus L, something along those lines. Well, that's a pretty clean expression. Let's go ahead and box that up. One of the things you'll notice here, right, is that the loan payment is proportional to the original loan balance. That makes sense. If I borrow $100 and I get a particular payment on there, right? If I borrow twice as much, I would expect the payment to go up by a factor of 2 because I just doubled the amount of money I borrowed. So I'm very happy to see this fact that the loan payment C is proportional to the loan balance that I took out. What else matters there? That value P, right? The thing that includes our interest rate, and then the loan duration L. Back to our student home loan. So we knew Y of -1 was equal to $400,000, something along those lines. We knew little p because it was a 12.68 APY or a 12% APR. It had a monthly rate of 1.01, and then we had a loan duration that was 30 years. That gave us 360 monthly payments, something along those lines. What we didn't know in this loan problem was what is C, and I can go ahead and make the calculation on that. This is going to require just a little bit of calculator work, so I'm going to go ahead and see if I can do that. I'm going to put 360 negative into my calculator, enter that. I'm going to have, I'm going to do this a little bit different. So 1.01, then 360, and I'm going to go ahead and raise that. And so that gives me a number. I'm going to take that from 1, and I get a number, and then I'm going to have 0.01, dividing that, and I'm going to 1 over that, and I'm going to take that times the loan balance, something like that. And what do I get here? I get my payment as being $4,114.45. Okay, so to finish this lecture out, I'm going to just summarize once again the two different ways that we commonly represent interest, and then do a final example that really highlights the difference between these two ways of representing interest. We have, as a first way of representing interest, annual percent rate. Annual percent rate really just says take your periodic rate, and then you multiply it by the number of periods per year. That gives us our APR. As an example, the one we just did, we said that there was a rate of 1% per month, and we know that there are 12 months per year, and that would give us a 12% APR. APRs, like I said, are typically used for loan type instruments, things where you are paying money to someone else. APRs tend to look smaller than the corresponding APY, which is the next one we'll talk about. APY is the annual percent yield. This one takes into account the compounding element, and it looks something like this. 1 plus the periodic rate expressed as a fraction. So 1 plus the periodic rate, and then we are going to raise that to the number of periods per year and subtract 1. So going back to the example we just had, if I had a rate of 1%, I add 1 to that, that's a 1.01. The 1 part of that, the overall 1 is the principal, the 0.01 is the periodic rate per month. We're going to raise that to the 12th power, and if you carry that out, you would get 1.1268. We'd already made that calculation. Subtract 1 from that, and what we get then from that is a 12.68% APY. So when we look at these two different things, even though they're both utilizing a 1% per month periodic rate, they really are going to mean the same thing. The APR given as a figure looks smaller, and the APY given as a figure looks larger. Banks wanting to make customers think that they are charging the least amount for loans will express all their stuff for loans in APRs. And in the same way, banks wanting to show they're giving the most to their customers for savings will express all their stuff in an APY. For me, I like to convert everything to an APY just because it more accurately reflects what I'm going to actually spend over the duration of the loan. So let's do one final example to really highlight the difference between these two. And I've got a story on this one as well. It is a true life story. So this is a true life example. Future Dr. Green's past high school friend, circa 1987. So I got a buddy that we went out for a Friday night of fun. and got hungry at the end, so we went to the Golden Arches McDonald's. A friend spied that dollar value menu hamburger sitting out there, stomach's grumbling, and definitely wanted that hamburger. Looking at it at the dollar value menu, it was a $1 hamburger. He opened up his pockets though, and he found out that he was totally cashless. Poor friend. So hungry, only $1 for a hamburger, but no cash. So he looks over at me and says, "Would you lend me a buck?" I'm always willing to help. So, of course, Honest Greens loans came into play, and I happily loaned my friend a dollar. But I did it in my own particular way. So let's lay out the basics of these loans and see what you think about this deal. So, what did I do? I lent my friend, the $1 for the hamburger, no problem. And I did it at 1/100th of a percent interest. Seems like a heck of a good deal, except I did that 1/100th of a percent interest compounded minutely. Compounded minutely. And believe it or not, yes, indeed, my friend did take this deal. Okay, so my question to you is, what do you think my friend owed me 1 week later when he decided to pay me? So 1 week later, okay, what does my friend owe me? Some other questions that we might ask is, what is the annual percent rate, right? What is the annual percent yield? Those are the figures that I would normally be interested in if I was going to be a true bank, something along those lines. So I just want you to take a minute and think about this. You borrow $1. It's compounded at a ridiculously low interest rate, 1/100th of a percent, but it's done so minutely. And it takes you a week before you decide to pay it back. You're not making payments, right? You're just going to pay a lump sum after 1 week and try to pay this loan off. Okay? So get a guess down, write a number down. I'm going to give you just 5 seconds. Make a quick guess. Let's go ahead and calculate out what my friend owed. 1 week later, when they came back to pay the dollar, okay, we need to figure out what in the heck does he owe. Well, we can do this as a simple calculation. I'm going to take 1. That's the principal amount. It's going to be scaled by 1, this whole thing, but we only borrowed $1, so that's fine. $1 plus what? We need to do a particular rate per period. It was 100th of a percent, so 1/100 times 100 to make it fraction. So 1 plus 1/10,000, right? That's a 100th of a percent added to the principal, and that would be how much would be charged after 1 minute. Well, there's 60 minutes per hour, right? There's 24 hours per day, and then there's 7 days per that 1 week period. So if I take 1 plus 1/10,000th and I raise it to the 60th, raised to the 24th, raised to the 7th, and I calculate that out on my calculator, what I get is $2.74. I would be surprised if many of you got even close to this number. I suspect that there was a wide range of guesses on this, probably thinking that I was out to be absolutely ridiculous, right? I don't know what you think about this. A dollar lent now for a hamburger when you're hungry now, and then a week later you pay back $2.74. I won't say that there's necessarily a lot of institutions out there charging rates per minute, but there certainly are some institutions out there, payday loans, for example, that charge some very interesting rates over very interesting periods. And in fact, I would say that many of them are predatory. So in this particular case, it wasn't like the friend couldn't afford it. He ended up paying a couple bucks for the privilege of having that hamburger beforehand. He survived the incident. Okay, but if we were going to put this in a better context, thinking about whether this is a good deal or whether it's maybe not a good deal, perhaps we should put this in terms of interest rates that we're all familiar with, things like APR, things like APY. So I'm going to go ahead and compute out the APR, the annual percent rate. If I was a bank and I was making a loan at 1/100th of a percent, compounded minutely, I would most likely lay out my APR as the figure of interest to see if I could attract a customer. So I want you to guess again. What do you think the APR is for this particular problem? Your credit card, for example, might be something like 18% or 22%. If you're a super, good credit risk, you might be down in the single digits somewhere. What do you think the APR is of this particular one? If we want to compute it out, we just go to the definition of APR. It says take the rate that we are doing for our period. We said it was 1/100th, so I'm going to do this calculation isn't already in percents. So it's 1/100th of a percent. And then we're doing what? We're going to multiply it by the number of periods per year. Well, there's 60 minutes per hour, right? Times 24 hours per day. And now instead of 7 days, we're going to do 365 days because there's 365 days per year. If I go through and do that calculation out, what we find is that the APR here is 5,256%. So that maybe makes this loan look a little bit less good, okay? They had a dollar loan. A week later, they owed me 274. Certainly, they could survive it in this particular case. But if I advertise this loan in a rate that would be typical of how institutions of lending do it, I would be saying that my APR is 5,256%. I don't think I'm going to get many customers this way, which is exactly why some of these payday loan places do not like to show what their APRs are. Well, we also know that APR shows a number as being somewhat artificially low, right? It's always going to be lower than that APY, and APY would be representative of what you would actually owe after a year. So let's go ahead and make the calculation of an APY as well. APY takes into account the compounding that goes along, and in this case, there's a lot of compounding because there's a lot of minutes per that year. And so let's go ahead and do the APY calculation. When I look at the APR, it looks bad, but it doesn't look like non-survivable bad. If I was a rich person, shouldn't I be able to handle that? If I was just a really rich person and I wanted to wait a year to pay this loan off, couldn't I handle an APR of 5,256%? Well, I think the answer really depends, right, on what's the compounding period. Here we have a short compounding period, so it's going to compound a lot. The APY looks like what? Well, we're going to take that one, that's the principal part, and we're going to add to that the percent interest per period. So the period here is a 1 minute. So I have 1/100th of 1%. So 1 over 10,000 added to that one. It's the same sort of calculation we did before, just now we raise it to 60 minutes per hour, right? And then I'm going to multiply that by 24 hours per day. So far the same. Now I'm going to raise that not to a 7, but to a 365. So raise that to 365, something along those lines. And if I go through and I calculate that out, what I get is I get 6.6892 times 10 to the 20th percent. What I can tell you is that this is absolutely gargantuan. It is astronomically large. If you took that $1 loan and you didn't pay it off in a week, but you waited a year, we could take that amount. So $1 would go to something like $6.6892 times 10 to the 20th. Okay, this is this end balance. This end balance is a trillion times. It's a trillion times more dollars. At least. It's at least a trillion times more. It's at least a trillion times more dollars than exists in the entire world. It wouldn't matter if you're Bill Gates or the most richest person on the planet. You could not buy a $1 hamburger at this 1/100th% interest rate compounded minutely and be able to survive the 1 year out payment. Okay, so that's enough for the lecture today. Next time we'll kind of return back to the topics of chapter 5, but hopefully this was a nice distraction and gives you some idea of some power of the Z-transform, some areas outside of maybe what we typically do in electrical.